pleasure to have Li-Cheng Tsai from Rutgers. He's going to be speaking about hydrodynamic large deviation principles for strongly asymmetric particle systems. So please, Li-Cheng.
Thanks, Sander, for the invitation, and thank you all for coming. At any time in the talk, if you have any questions, please feel free to ask me. So this is a joint work with Jeremy Quastel, who I believe gave a talk a few weeks back in this seminar. So the title is about hydrodynamic large deviations for strongly asymmetric interacting particle systems. But actually, I'm going to talk about one very specific interacting particle system, which I'm going to define shortly. It's the asymmetric simple exclusion process. So it is a process where you have particles on the one-dimensional integer lattice. Now, each of these particle attempt continuous time random walk with rate L one step to the left and rate R one step to the right. So each of these particles carries their own +1 clock, and whenever the clock rings, the particle decide whether they want to jump to the left or right with the rate. Under the exclusion rule, what does that mean? It means that each side can hold at most one particle. So for example, if you look at this side, when this particle wants to jump one step to the right, it's been told no. So to give up the jump and then wait for the next one. Okay, so that's a fairly simple dynamics. And let me just flush this out. So one thing that's going to be useful throughout this talk is this quantity called height function. Okay, so it's just a convenient tool to encode the configuration of particles. So the way to define is as follows. Whenever you see a particle, you draw a line with slope +1. And whenever you see a hole, you draw a line with slope -1. And then plus, minus, okay, and so on and so forth. So each particle configuration corresponds to a height function and vice versa. If you gave me a height function like that, I can derive that particle configuration. And if you think about it, the dynamics of particle jumping left and right corresponds to having this local mean flip into local max, or local max flipping into local mean. Okay, all right, so that's just a technical note. So there are many questions that you can ask about the ASAP, the asymmetric simple exclusion process, and we're going to be interested in their large scale behaviors. So imagine that you take a huge chunk of these particle systems. It's infinite particle system because it's on the integer lattice. You take a huge chunk of them and you look at it from far away, kind of zoom yourself out of it, okay? And also at the same time, you run this dynamics for a long amount of time. And you want to see if there's some, pattern, overall deterministic shape that would arise as you do this kind of scaling or zooming out, okay? So now classic result in the field of hydrodynamic limit says that if you take this particle system, you scale the height function accordingly, or put it differently, you zoom out by a lot, then the height function gonna converge to some deterministic shape, and the time evolution of that height function is described by the solution of a partial differential equation, and these kind of PDE typically are related to hydrodynamics, and hence the name hydrodynamic limit. And a closely related question of hydrodynamic limit is the question of large deviations. And I'm going to tell you a little bit more about it. Just as for now, I just tell you that they're also related to partial differential equations. Okay, so this is a rough description of the question that we're interested in. So let me go one step further and tell you that there are two different kind of types of particle systems now people have considered. One I call weak asymmetry, and the other one is strong asymmetry. So in the current context, it depends on how you tune these parameters L and R. When L is equal to R, that's co-symmetric because the rates are symmetric. And what you could do is, you introduce a small amount of asymmetry. So you scale the lattice by 1/n, or put it differently, you zoom yourself out very, very far away, okay? And as n goes to infinity, you can scale the asymmetry by 1/n, and that n goes to infinity. And if you do this, the resulting kind of time scaling would be n squared. So time scaling would be n squared, so it's parabolic, it's like random walk. And the corresponding hydrodynamic partial differential equation is going to be parabolic. It's going to have a second derivative in space and first derivative in time. And the large deviation principle, which I'm going to tell you a little bit more about, is what I call friend and vessel. It's like the large deviation principle, the simple past large deviation principle for the Brownian motion or for diffusion. Okay. On the other side of the panel, I can do something different. Instead of tuning the asymmetry to 0, I can keep the size of the asymmetry positive, strictly positive. And the behavior is quite different. Okay, so first of all, the scaling is going to be hyperbolic. If you fix the asymmetry positive, being strictly positive, the time scaling is going to be n, the same as space. Okay, and the limiting PD that you can get is fully nonlinear hyperbolic. And the large deviation principle is going to be described by something called Khrushchev entropy production. I'll tell you a little bit more about what that means. Okay, so just to give you some heads up. Okay, so in the next few slides, what I'm going to do is I'm going to walk you through the hydrodynamic limit and the large deviation principle of the weakly asymmetric particle system, and more specifically, the weakly asymmetric ASEP. And then moving on, I'm going to contrast that with the strongly asymmetric side, the strongly asymmetric, actually totally asymmetric simple exclusion process. All right. So here it is. So if you look at the weakly asymmetric simple exclusion process and you do the scaling I told you earlier, and as I told you earlier, the scaling that you're gonna perform on height function is going to be parabolic. Okay, so parabolic in space and time, and the height function is going to scale by n. And if you do this kind of scaling, you take n to infinity, what's going to happen is that the random height function, the random evolution of the height function, is going to converge to something deterministic. What is that something deterministic? It's going to be described by the solution of this PD. Okay. And for many of you in the audience, you're probably more familiar with the density instead of the height function. So equivalently, you can take the x derivative of the height function that corresponds to the empirical density of the distribution of the particle. And if you take x derivative of this PD, you get the famous Vickers-Burgers equation. So what this result is saying is that if you wait long enough and look at far away enough the particle system, then the evolution of the density is going to evolve like some sort of fluid described by the Vickers-Burgers equation, or the height function is the integral. Okay, this result is due to Kipnis, Olah, and Varidan. Let me just give you a heuristic. It's really not rigorous explanation of how such result could be true. Okay, so let me just give you a quick sort of heuristic. So, as it turns out, if you go back to the slide where we define ASEP, you look at the dynamics and you really just sit down and really write down the dynamics. More precisely, if you look at the actual height function, you try to see how it can change, whenever a particle jumps. Then after some amount of work, which I'm not going to do, you can write down the sort of discrete dynamical equation for the height function. Okay. And there's some algebra you need to go through. You need to simplify things and do a little bit of work. But this is what it comes down to. Okay, so the first term is a discrete Laplacian. Okay, I'm not sure if I defined it. Did I? No, I didn't. Sorry. So let me write it here. So the discrete Laplacian is 1 over n squared, f of x plus 1 over n plus f of x minus 1 over n minus 2 f of x. So it's the lattice version of Laplacian, and grad n minus is the lattice version of gradient. And similarly for nebula minus. Okay, so if you look at the first, again, this comes after some simplification, which I'm omitting here. So if you look at the first two terms on the right-hand side, they look very similar to the PDE that we're looking at, right? So if you were to just not very carefully replacing this discrete Laplacian and discrete gradient with the continuum one, you would get the PDE that we're after. But there's an extra thing, right? After all, this process is random. It has to be something random coming out of this equation. It's being encoded in the last term here, where m is a martingale in time. So for each x, this is a martingale in time. And for different x's, they are independent. And the quadratic variation is something that can calculate explicitly to be this quantity. So what does this m look like? Well, because it's a martingale in time, they're independent over different sites. So it's not hard to imagine that this m gonna behave like a space-time white noise in the large n limit. But in front of that, there's a 1 over square root of n factor. So you can imagine that as n goes to infinity, this guy just died. Okay, so very non-rigorously, you can just try to approximate the evolution of the actual height function by this. Okay, so the first part again is the same PD that we're after, and the second part is just a small noise, a small driving noise. And as n goes to infinity, you could imagine that the thing goes to 0, and hence, we arriving at this PD. Okay, so that's a very heuristic description of how such a result could be true. Any question up until this point? All right, we still let me know if you have any questions. All right, so that's that's the hydrodynamic limit. Now, what about large deviation principle? So before I jump into it, let me just very quickly recap what, in a very informal fashion, what is a large deviation principle in the current context. Well, so we know that with high probability, the scale height function gonna look like this deterministic solution of the Burger's equation or the integral of that equation. So now I ask a different question. What is the probability that I see a very unlikely realization of the height function instead of following the solution of the PD of Burger's? What is the probability I see a different h, where h is a generic height function? Right? What is the probability of that? Well, the probability is typically small. So in this example here, it's going to be exponentially minus n. The speed or the scale as e to the minus n. Now, we're not only interested in the scale, we're also interested in extracting the prefactor in front of the exponentially small probability, which is to say that for different kind of, even though these deviations are very unlikely, for different deviations, the degree of unlikeliness are different. They carry different prefactors. So extracting this quantity, which is, as you know, the rate function, is more or less the goal of large deviation principle. So for the case of weakly asymmetric ASAP, the large deviation principle was proven by the same paper of Kipnis, Ola, and Verity. Okay, so here's the result. So it satisfied the large deviation principle with this rate function. Okay, now this looks pretty complicated, so let me try to walk you through it. Okay, so the first thing to notice is that in this rate function, there's something I call rho. It is a sort of the control function, so to speak. So rho is a function of space-time. So what do you do with rho? Well, you look at the same PDE, the integral of Burger's equation as before, but you add to that PDE this rho. You think of rho as some sort of driving force. So you drive the PDE with this extra term, okay? And that gives you a solution which I call rho, h of rho, or h of rho tx, that as a function of space-time. So what you do is, I give you a generic deviation, and you try to tune the rho so that the resulting h of rho approximate that h, right? So you try to tune this control so that the resulting deviation can be achieved by solving the Burger's equation with this rho. And once I found that rho, I give it a cost, which is like the cost of L2, which is like an L2 cost, 1/2 of rho squared, except that it's being multiplied by this funny function rho, sigma. So how do I understand this? Okay, I hope that explains what the rate function is. But how do I understand this? Well, for that, I'm going to take you back 2 slides before. Okay, so this is the equation that we wrote down when we talk about hydrodynamic limit, right? And I told you earlier, because this 1 over n squared factor, the noise term is going to die out as n goes to infinity. But now we're talking about large deviations. So the noise might behave atypically, might do something that it won't normally do. So one thing that it could do is instead of going down to 0, it goes up very big. So it is with exponentially minus n probability, there's a chance that this thing could contribute something large, and its contribution is being recorded by that function rho I wrote earlier. Okay. Now, if you stare at this equation again, it looks exactly like this. So really, this is capturing what happened in the discrete equation when the noise or the martingale, performs some atypical deviation, which is described by this control function rho. And what about the cost? What about this thing here? Well, the cost, if you go back to look at this, I said this thing looks like a noise, right? So if this really is a space and wide noise, you just pretend that it's a space and wide noise with this additional quadratic variation written here, then the rate for that thing is given by the L2 norm multiplied by that function, sigma. Okay, so this is like the rate function for Brownian motion, which is the L2 norm of the derivative. Okay, so this is a very heuristic way of describing the large deviation principle of asymmetric, weakly asymmetric simple exclusion process. And this is what I refer to as friend and Vassal. If you know the standard theorem by friend and Vassal on the large deviation of diffusions, then this looks very similar to that. Okay, it's also being controlled by a control function that describes the deviation of the underlying noise. Okay. Now, before I finish this slide, let me just make a remark that the hydrodynamic limit and this kind of friend and Vassal LDPs under weak asymmetry have been established by many authors for many different models. The field is gigantic, and if I try to list the number of authors, it would probably more than fit this page. So let me just mention that there are a lot of results in this vein which I did not list, many of which are done by the people in the audience. Okay, so this is the story about the large deviation and hydrodynamic limit for the weakly asymmetric system. Any question up until this point?
Just quick question. Sigma is actually U minus U square, yeah?
U minus U square. Not because, okay, it's a little bit different. So U minus U square is if I choose U to be between 0 and 1, right? But my U here is actually minus 1, 1. So there's a shift.
Sorry, I had lost the change of variable. Sorry. Okay. Thanks. Thank you.
Yeah. Yeah, it's a little bit annoying. I can't fix my mind which convention I like to choose, but that's the convention we end up using, which is not always standard. Yeah. Any other questions? All right. So I'm going to head into the universe of strong asymmetry. Okay, so for that, I'm actually going to specialize for, instead of looking at general strongly asymmetric particle system, I'm going to look at the totally asymmetric simple exclusion process. So a particle only jumps one step to the right. Okay, it doesn't jump to the left. Okay, in continuous time. So here's a model. So we're going to talk about TASEP, totally asymmetric simple exclusion process, hereafter. Okay. So as I told you earlier, the scaling in this context is hyperbolic. So you scale everything by n. The height is space of time. Okay. Now you can try to go back and do the same calculation I told you earlier. Write down the discrete equation for the height function and do the scale. And we go through. The only thing that changes is obviously scale. So previously, both the noise or the martingale term, previously only the martingale term goes to 0. Now, if you look at hyperbolic scaling, both the Laplacian term and the martingale term go to 0 because they carry some small factor of 1 over n. So informally, non-rigorously sending n to infinity, you could imagine that the limiting PDE is like this, right? It's just, you look at the discrete equation and you wipe out those things that should formally go to 0. That should be your PDE. And this is indeed the result, okay? So the result by Razzacano and later by Saplanian says that if you scale H, the totally asymmetric simple exclusion process hyperbolically as n goes to infinity, the height function converges to the solution of this fully nonlinear hyperbolic equation, or you can take the derivative, is the inviscid Burgers equation. Now, so what's the difference? Well, for those people who are familiar with inviscid or fully nonlinear hyperbolic equations, you know that solutions or weak solutions to these equations are not unique. So previously, when we're talking about parabolic equations, because of the existence of the second derivative, because of Laplacian, the solution is nice, it's smooth, and the solution is unique. However, moving into the fully nonlinear case, the solution to such PDE are not unique. And in order to uniquely identify a solution, you need to impose an additional assumption, which is called an entropy condition. Now, there are various ways to impose the entropy condition. We'll get to one later in this talk. Okay, so just remember that in order to deal with this kind of fully nonlinear equation, you need an extra bit of information to specify the solution. So the full results here says that as n goes to infinity, the scaled height function for TASEP goes to the entropy solution, the unique, the physical solution given by the PE. Now, for those of you who are familiar with hydrodynamic PDEs, this looks very similar to what's called the vanishing viscosity limit in that literature. So what is vanishing viscosity limit in PDE? It means if you, for example, you take the Vickers-Burgers equation, the one with the second derivative, and you tune the second derivative, the Laplacian, with a small parameter down to 0. What's going to happen in the limit is that the solution of the Vickers equation is going to converge to the entropy solution of the inviscid Burgers equation. Okay, so the Laplacian, even though it vanishes, has the effect of picking out the unique physical entropy solution. And this is similar to what happens here, right? So in the discrete equation, you have this discrete Laplacian term, which formally vanishes in the limit. However, it doesn't actually just go away. It has the effect of picking out the unique physical entropy solution in the hydrodynamic limit. So this is one thing I want to highlight. This is sort of the quintessential contrast between the strongly asymmetric world and the weakly asymmetric world. In the weakly asymmetric world, you basically see the impact of every term in the equation. And in the strongly asymmetric world, mysteriously something goes away, like the Laplacian, but they leave an impact in an indirect fashion. In this case, they leave an impact by choosing the entropy solution. Okay, so that's the story for the hydrodynamic limit. Okay, so moving on to large deviations, how do we understand the large deviations of the TASEP? And for that, I'm going to look at one special case. So let's just consider one special initial condition, which is called step initial condition. What is that? All the sides to the left of the origin is filled with a particle, and all the side to the right of the origin is empty. Okay. So if you plot the density, and remember my convention is plus minus 1, the density is 1, constant 1, all the way to 0, and then jump to minus 1. Okay, so that's the initial density. Now, if you just let the thing evolve, what's going to happen? Well, think about TASEP. TASEP is what? TASEP is particle jumping one step to the right? So this is like a traffic configuration. Each of these particles would attempt jump to the right. So as you release from this initial condition, particles are going to move to the right and going to dissolve gradually. So it's not hard to imagine that the density would sort of goes down in the middle part. And in the far left, far right, they remain what they were, plus 1 and minus 1, fully occupied and fully empty. Now, if you plot out the characteristic lines, it looks like this. So what is this figure? Each line in this figure is a line in space-time on which U is constant. So each of this line, if you go along each of this line in space-time, you'll see that the density U is constant. So initially, the density was plus 1 and minus 1, or I should probably say 1 and 0, but my convention is plus 1 and minus 1. And it kind of just propagate out. Okay, so in the middle region, you see where the density would go from plus 1 to minus 1. And in the far left and far right, there's remain plus 1 and minus 1. So this is what it looks like. All right, so how can we perturb the process so that it doesn't do this, right? So what I just described to you is the hydrodynamic limit. It's a solution of Burger's equation, the inviscid Burger's equation. It's what I typically see if I release a particle from such initial condition. This is a typical behavior. How can I see an atypical behavior? How can I generate something that is unlikely to happen? Well, if you think about the TASEP as some sort of traffic system, right, where particle goes from left to right, one way to perturb the system is to perturb the traffic, to slow down the traffic. So one thing that I can do is I slow down a few sites around the origin, which is a bottleneck, right, which is where every particle has to go through. So once I do that, what's going to happen? What's going to happen is that it's going to cause a jump of density at the origin. What's going to happen is that it's going to cause this constant jump of density to the left and to the right of the origin. And this is, this of course depends on exactly how you slow down a few sites. You can slow down just one site, or you can slow down a handful, 3 or 5, 6 number of sites around the origin. However, as long as you do this, what you're going to see in the profile of the hydrodynamic limit is that you're going to have a constant size jump at the origin. And in terms of PDE, in terms of fluid dynamics, what that does is it causes a non-entropy shock at the origin. So if you look at the characteristic line, as we showed before, you'll see this interesting bifurcation at the origin. So put it differently, if you look at the space-time trajectory of the characteristic, you'll see that at the origin, some characteristic lines are being sort of generated, sent out from the origin. And this is what's called non-entropy shock in the context of fluid dynamics. And the result I told you here about the shape and this non-entropy shock was proven by Landing and Sablanian for various different ways of slowing down the origin. Okay, so what do we learn about this? Well, what we learn is that if you do this kind of deviation, then the resulting configuration is still going to be a weak solution of the same equation as Burger's equation. What changes is that the solution was entropy. The physical one was entropy. Whereas in the larger deviation region, the deviation now becomes a non-entropy solution of the same equation. All right, so let me just summarize that. So first of all, let's ask ourselves, what is the scale? What is the speed of deviation? How unlikely is such slowdown going to happen? Well, every time you slow down, it costs you some probability, say a half. Okay, every time somebody tries to jump, you say, with probably a half, you're not going to jump. So that costs you some probability. How long do you have to do this? You have to do this throughout the entire time span. So remember, the time scaling is n. So the probability is e to the minus the size of the time span, which is e to the minus n. So that tells you the speed is still n, e to the minus n. That's the speed of deviation. Well, what about the space of deviation? What are the kind of deviation they're going to see? Well, this example suggests that the deviation should be a weak solution. So it is possible that the hydrodynamic limit gives you the entropy solution. And in the world of larger deviation, what you're going to do is you're just going to pick one of the other non-entropy solutions. Okay. Right, so that's sort of a speculation based on what we have seen. It turns out that this is the case. Okay, so a paper of was studied by Jensen and Verdun in the early 2000s. They showed that up to super exponential O probability, which is the relevant scale that we're interested in, the empirical density of the TASEP concentrate around weak solution of the inviscid Burger's equation. So this theorem verifies the speculation I told you. It is the case that all the deviations essentially happens within the space of weak solutions. Okay, so that tells you the speed, that tells you the configuration, the space. What about the most important thing, the rate function? Okay, in order to introduce a rate function, I need to do a little bit of preliminaries. So this slide is about Kirchhoff entropy production, which will be relevant for defining the rate function. Okay, so let me walk you through this. Okay, So in the context of Korsakoff entropy or Korsakoff entropy production, there's a strictly convex function, which is thought of as the entropy. So it's a generic strictly convex function, I, which we thought of it as an entropy. And this convex function goes from -1 to R, which is the range or the range of the density, okay? Now for each given such entropy or convex function I can define what's called entropy flux this way. Now, why is it called entropy flux? Well, you can check that if U is a smooth solution, it's a smooth solution of the Invisburger's equation, then we have this by just using calculus, chain rule essentially, that you have this equation. So the tidal derivative of the entropy is given by the x derivative of the entropy flux, and that's why the thing is called entropy flux, right? This is how you get a conservation of entropy. However, this calculation assumes that U is a smooth solution. But in general, we know the solution of inviscid equation could be non-smooth. So what happens? Well, in that case, you can do a back of envelope calculation. Now just look at the simplest case where the solution U has a jump discontinuity, and the jump discontinuity corresponds to having a shock, okay? And there are two ways that you can have a shock. One is the left density is smaller than the right density, and the other one is the other way around. One of them corresponds to entropy shock, and the other one corresponds to non-entropy shock. If you go back to, probably 2 slides back to where I show you the non-entropy shock, you can check that it is this scenario here. The left density is higher than the right density, okay? Now, just look at this simplest case where U is constant on both ends and there's a jump. And you can try to calculate this quantity, and you'll see that in the entropy case, this total flux is negative, and in a non-entropy case, this total flux is positive. And in fact, this phenomenon is more general. It goes beyond this very simple example. So there's a theorem in fluid dynamics that says for any given initial condition, there's exactly one weak solution such that this quantity is always non-positive, right? So put it differently, as soon as I know this thing is everywhere non-positive, that solution is the unique solution, which we can define to be the entropy solution. So this is one way to formulate the entropy condition. So this quantity, this requirement here can be taken to be an entropy condition. So on top of the PD, if we impose this constraint for some given entropy I, then there's exactly one solution. Okay. Now, with this in mind, it is hence natural to try to characterize how non-entropy a given solution is by the positive part of this quantity, right? So positive part of this quantity. And that's what Jensen-Verdun did. So you take a specific I. Before this slide, the I was a generic convex function. Here I'm going to take a specific I, which I call I Bernoulli, which is this. Now, this is the rate function for sums of RID independent Bernoulli random variables. So this I is a particular one coming from the large deviation for RID Bernoulli random variables. If you take this as your entropy and you construct the corresponding entropy flux, and you integrate that, you take the positive part of this. This thing is what Jensen and Verdun postulate to be the rate function for the TASEP. Okay, so why do we take the rate function for I Bernoulli as the entropy? Well, the reason is that TASEP, or more generally, any constant speed exclusion process has the product Bernoulli stationary distribution. What does that mean? So let me just draw you a picture. So we have exclusion process. Okay, in this case, it's TASEP. Maybe I shouldn't draw a dot on the integer lattice. Now, if I prepare a configuration by just independently flip the same coin with probability row, if it comes up head, I put a particle. If it comes up a tail, I put no particle, and so on and so forth. Okay, independent Bernoulli generated particle configuration, and run this particle configuration by the dynamics of TASEP or any constant speed exclusion processes. then the probability distribution is invariant. So this is invariant distribution for the TASEP, and hence it is at least not too gratuitous to take IBER as our entropy function. Okay, so this is the proposed rate function. All right, so we have every parameter. We have the speed, we have the rate function, we have the space of deviation. Do we know about the actual large deviation principle? So here's a known result. So in the same work by Jensen and Verdun, they proved that TASEP satisfies an LDP with, an LDP upper bound, not the full LDP, just the upper bound, the bound that bounds the probability from above with this rate function. So roughly speaking, that is the probability of Hn approximately equal to H is approximately less than equal to e to the minus n I Jensen-Verdun. Okay, so that's the LDP upper bound in a slightly non-rigorous way. Okay, so we know the upper bound. What about lower bound? Well, lower bound for some special weak solutions are being derived in Jensen-Verdun and later in Valencia. Now, a natural way to sort of complete the proof following the result of Jensen-Verdun is to try to find a lower bound that matches the upper bound. However, remember I told you that the space of deviation is the space of all weak solutions. So in order to really complete the scheme, what you need to do is to find the matching lower bound around any weak solution of the Burger's equation. But that is not a very well understood object. We don't really know what all the weak solutions of the Burger's equation look like. Okay, so the desire to complete the scheme by Jensen-Verdun has prompted the development of many work in PDEs, in analysis, to investigate properties of general weak solutions, which I'm listing here. And there are many interesting results in this study. Now, in different direction, people look at different models. So instead of TASEP, you can look at random PDE, or there's something called a PD version of the same problem, which I don't have time to discuss. Roughly speaking, you reformulate this large deviation problem as some sort of variational problem, and you try to minimize that quantity, and that's sort of a PD version of the same problem, which is carried out in this work. And this is a different model of the same problem. Okay. Now, all these results have a common feature, which is that you'll be able to prove the full upper bound, the full large deviation upper bound. But for the lower bound, you have to confine yourself to specific weak solutions. And the ultimate reason is the same thing. It's just because we don't have good enough control of a generic weak solution of the Burger's equation. So these are the known results. And the result I'm going to show you in this talk, which is a joint work with Jeremy Quastel, is how we prove the full large deviation principle for the TASEP. Now, the rate function that we prove is not exactly the Jensen-Verdun rate function. It's sort of a slight modification of it. What is that? Well, we took the Jensen-Verdun rate function, but instead of just evaluating it as a generic weak solution, we take the limit inf along a specific class of weak solutions, which we call LM. LM stands for elementary, is a specific class of nice weak solution, which I'm not going to tell you the detail, but they are. Okay, and that's the rate function. I prove that TASEP does satisfy the full large deviation principle under this rate function. So let me just quickly remark that compared with Jensen-Verdun, we didn't actually improve the lower bound. Jensen-Verdun could have done this using the method, right? Because these are special weak solutions. So for the lower bound, it's really not very different from what has been done before. The major improvement here is actually the upper. We say that in order to get the upper bound, you don't have to minimize over all possible weak solutions. You just need to look at those good weak solutions. So we bring the upper bound closer to the lower bound, not the other way around. Okay. Actually, any questions? This is the result. All right. So let me just briefly outline the result the method that we use. So our starting point is very different. It's almost completely different from previous work. So, in this context, hydrodynamic large deviation, it's natural to start with probabilistic or analytic tools. But recent development in integrable system actually points a new way to proceed. In particular, this paper by Matetski, Quastel, and Remenik in 2016, they essentially completely solve the TASEP. What does that mean? If you start the TASEP from a generic initial condition and you look at its transition probability at a later time, they found an exact determinantal form. It's a Fredholm determinant, explicit, that express this probability explicitly. So what we did is we took that formula and we hit it very hard with our hammers, and hopefully that something will come out of it. And something did. Okay, so it turns out that if you analyze that exact formula careful enough, you'll be able to extract what I call finite dimensional large deviation principle from that formula. So you can get finite points, large deviations. And I can imagine that once you can do that, you can approximate the full large deviation, space-time large deviation, by just taking more and more points. Okay. Well, that finite dimensional large deviation principle is encoded in some formula. So there's one more thing that you need to do is to match that formula to the Khrushchev entropy production proposed by Jensen and Barrett. Okay, so once you can do that, then it should follow that the things satisfy the full large deviation principle. Does that make sense a little bit? All right. All right, so for the remaining time in this talk, I'm going to walk you through the proof. I don't know how far will I get, but let me just try. I never actually finish all the slides in this talk. So let me just give you a taste of what the proof is like. And for that matter, I'm going to consider a special initial condition. First, our favorite initial condition, the step initial condition. Okay. So all the particles, all the sites to the left of origin are filled with particles, and all the sites to the right of origin are empty. If you look at the height function, remember height function has slope 1 when there's a particle, slope -1 when there's no particle. So the height function is this wedge minus absolute value of x. Okay, so that's the initial height function. So I'm going to run the thing for some time t and look at the large deviation in space as that later time. Okay. So before I do that, let me tell you what is the hydrodynamic. Right? So instead of large deviation, what is the shape they're going to see for the height function at a later time? And this is something that I can calculate. This is essentially the solution I showed you earlier. This slide, this solution. If you write the height function, that was for the density. If you write out the height function, it's exactly this function. It's, you don't have to pay close attention to what it is. It's just explicit. Okay, and its figure is being shown here. Okay. So what is the question that we're interested in? We're interested in, well, what is the probability that the TASEP doesn't do this blue curve? It does something atypical, not the blue curve. More precisely, I'm going to fix a number of points. X1, X2, X3, and condition on atypical value of those points, at those points. Right? What is the probability that the height function, instead of doing the blue curve, it does this point, and does this point, and does this point, at these 3 points? What is the probability that goes through around these 3 points? Now, one thing I want to point out is that you notice how I always put the point above the parabola. You might be thinking, why do I have to do that? Why can I not put the point below the blue curve? And the reason is that the reason can be explained in 2 different ways. Okay. So one thing is that if you try to reach a point below the blue curve, you can show using probabilistic argument that the probability is way too small. It's e to the minus n squared, not e to the minus n. Okay. So going back to the traffic interpretation, where particles going from left to right, going down below the blue curve correspond to having to speed up the traffic. And it's not hard to convince yourself that in order to actually speed up the traffic in a significant way, you need to pay e to the minus n squared probability, not just e to the minus n. Okay, so that's a probabilistic explanation. Now, if you prefer a PD explanation, it is possible to show that as soon as you probe below the blue curve, there's no weak solution whatsoever that will reach that point. Okay, so in order for the configuration to stay within the space of weak solution, you have to be above the problem. Okay, sorry, not the blue curve. By problem, I mean the blue curve. All right. So what is the probability? Well, the probability is e to the minus n. It's approximately, let me write it down. Is approximately e to the minus n I star. The precise result is in this proposition. Okay, the probability is approximately e to the minus n I star. What is I star? What is the rate? Well, the rate is given by this explicit expression. Well, okay, what does this explicit expression mean? Well, it has a nice probabilistic interpretation. It says that in order to see a deviation G in space, where G sort of parameterize a possible deviation in space at a later time, the rate I have to pay is given by plugging the Bernoulli rate of the derivative of x minus the Bernoulli rate of the parabola. So what does that mean? It means it looks as if I'm doing a random walk, a Bernoulli random walk that is conditioned to stay above or equal to the parabola. And the rate of that gives me the rate of the spatial, fixed time spatial deviation of the TASEP. Okay, so let me just try to describe it in a more sort of vivid way. You imagine this is the parabola. This curve here is the parabola. And imagine that's solid. Okay. Now imagine that you put a rubber band on top of this parabola, and then you put a number of points, x1, x2, x3, above the parabola. So you pull the rubber band up, up this parabola. And you'll see this curve here, this trajectory which I call G star, is the one that minimizes energy. That is the most preferred, configuration under such a condition. And the amount of energy costs you to go from the parabola up to those points, which is given here, is the rate function. Okay, so that is the result. Does that make sense? The result itself, the statement of the result. All right. So let me just say a few words about how we prove it. And as I said earlier, this is done by extracting the rate from exact formula. So for the wedge initial condition, you can use MQR, but the formula actually goes back to Johansen and for different, slightly different model by Professor Schwab. Okay, but anyway, take one of those exact formula. Actually, I have a typo here. My apology. There's no log here. Just ignore that. Okay, so take one of those exact formula. It says that if I look at the probability of the height function of the TASEP underneath those dots, it's given by explicit Fredholm term. Okay, it's determinant 1 plus kn. And kn is very complicated. I don't bother to write down. But it's explicit. It depends on these parameters, and it's a trace class operator acting on little L2 space. Okay. Now I don't assume everyone here knows familiar with Fredholm determinant. So here I'm just going to give a very quick impressionist definition of Fredholm determinant. It's defined as the infinite series this way. The first term, the zeroth term is 1, and the first term is a trace of that operator. And the second term is some sort of a quadratic trace, and the third term is sort of a cubic trace. So it's by definition this series expansion. Okay. So how do we analyze such a thing? Well, it is actually pretty well known in the literature of random matrix theory and integrable system that if you look at just one point, instead of conditioning 3 points, for example, if I look at just 1 point, then this Fredholm determinant behaves in a very nice way. What way? Well, the trace term, the first term, is much smaller than 1, and the quadratic term is much smaller than the linear term, and the cubic term is much smaller than the quadratic term, and so on and so forth. They're nicely ordered. As n goes to infinity, the first one is 1, the zeroth one is 1. The first one is leading order, so to speak, and the second one is much smaller, and so on and so forth. So if this is the case, it is easy to calculate to extract the asymptotics. You just need to estimate the trace. Okay. So for m equal to 1, this is an easy case. Now, unfortunately, when m is bigger than 1, this is no longer true. So if you write down semi-expansion and send n to infinity, you'll see that sum of terms in the expansion is divergent to infinity, and that is terrible. So we don't want that because we're trying to get large deviations. So everything should be exponentially small, but instead of exponentially small thing, you get some exponentially divergent thing. However, if you just look more careful, for each such exponentially divergent term, if you look deeper into the series, mysteriously, there's always something that is also exponentially big that exactly cancels this guy. So what actually happens is that there are many, many delicate cancellations in these series when m is bigger than 1. And the way we proceed is just to, brute force exhibit those cancellations. So for every bad term, we find another term to cancel. And the argument is combinatorial in nature. As you can imagine, it forms the bulk of this work, which I'm not going to discuss, just to give you an idea how the proof is done. Okay. So that explains very roughly how we get the result for the wedge initial condition. But there's still one thing I didn't explain to you. How do I match such a random walk rate function, which has a nice probabilistic interpretation, to Kushkov entropy production, right? This is something that we're after. Okay, so let me just draw you a cartoon of the situation. Remember, we're looking at fixed time large deviation principle, right? So this is space, this is time, and we're fixing. I should just call it time. Now look at a fixed time deviation of the thing, and the random walk rate function is given by a G star at the terminal time t, right? What I need to do is to try to relate this fixed time quantity to a space-time quantity that evaluates the Kushkov entropy of some weak solution. Right? So I need to find out, I somehow have to engineer a weak solution such that its Kushkov entropy production will match this random walk function. How do I do that? Well, the answer turns out to be surprisingly simple. What you need to do is you take this terminal deviation G star and you run it backward in time by the entropy solution of Rutgers. That is the weak solution that will give you this entropy production. So 2 quick notes. If you take a backward weak solution of Rutgers, it's automatically a weak solution of the forward equation. Okay, so if I run the thing backward and look at it in forward time, it is a weak solution. However, a backward entropy solution is generally not a forward entropy solution. Right? So if I run this thing backward by entropy evolution, it's actually not a weak entropy solution of the forward equation. Okay, and this statement here that you can match this random walk rate function to the Kushkov entropy production is really a special case, a manifestation of what's called the Onsart-Matchlob principle. Okay. So, any questions so far? All right. Let's see. All right. I think probably a good idea if I just stop here. I have a few more slides, but I don't think it's instructive to finish them all. And if you don't mind, I can just stop here and take questions from this point on.
Okay, well, thanks very much for a very nice talk, Li-Cheng. Let's thank the speaker. Could I ask if there are any questions from the audience? Well, I have a question maybe to warm up a bit. Maybe it's an obvious question. So you mentioned the class elementary or LM. Can you say a little bit more about what is in that set?
Yes. So in this case, I just discussed. This is G star, right? It's this rubber band thing, and the weak solution that corresponds to this G star is you run the thing backward in time, and you can write down by quote unquote write down fairly explicitly what that is. So this is one example of elementary weak solution. And the question is, how do you generalize this to other initial conditions? And the way we did it is we take a union of finitely many wedges. Right? Instead of just one wedge, you took finitely many, and you assign these points to, for each of these points, you assign it to one of the problems. And you do the same thing, and you take the max. You can show that this is a weak solution. And the union of all such things is what we call LM.
I see. So I have another maybe could be obvious question. In the beginning, you mentioned partial asymmetry, ASEP, and things like this, where you can go left. How does that work in this context?
You mean in terms of exact formulas, or?
Well, do you think that the result is the same? Maybe just with
I see. Yes.
with a constant p minus
right.
2.
So in general, one would expect large deviation principle to be universal. So it is plausible that they're different. However, the kind of large deviations that we're looking at, they're pretty robust. So here's the conjecture. If you look at any finite range, constant speed exclusion process, and up to some parameter rescaling, as long as it's asymmetric, it satisfies the same large deviation principle. And actually, you can go one step even further. You look at different models of similar taste. It's a little bit vague. The large deviation principle is being described by two things. One is the PDE, the hydrodynamic PDE, and the other one is this I. How do you choose this I? Well, you just look at the invariant distribution. If the invariant distribution is explicit, you can analogously write this down. And that's the conjectural LDP.
Yeah. Maybe I'll stop and I can ask him more, but maybe if there are others who might have a question, yeah, please.
So could you go maybe back to slide 27, I think it was, or something like this? Sorry, forward. No, it's after that, 27, maybe it was, yeah. Just like the form, yes, yeah, here, exactly. So, because what I understand is that you have a very sharp description of this probability. Actually, you have an explicit description. You have this probability that hn of txi is less than I. It's an equality with this determinantal expression, right?
Right.
But as I understand, however, there is no 1 over n log sure. So the very first line of this statement here, I think this can be proved for, say, changing the right entropy and so on for a few models where maybe you don't need really the exact formula, and still you can have this very first line where, like the equivalent, like that the probability that you're close to a reasonably good solution, like element here, it has the right expression. You understand what I mean? Like the probability.
Okay. I think.
But so my question is: do you need like these exact expression, these integrability features, for the next step that you didn't have time to discuss, namely from this statement to the full large deviation principle?
Well, I think there might be a miscommunication here. The rate, this proposition I'm stating here is for if I only condition at finite number of points. I do not constrain the rest, right? Let's just consider 1 point. It is, as far as I know, without using integral means, it's difficult to argue that even that what happened outside of that point, right? You have an explicit conjecture of what it should be. It should be that, that rubber band. But if you don't use probabilistic you don't use algebraic argument. I tried it. I think it's very difficult to actually prove that. The optimizer, you can prove that this thing produces a right wave function, but it's hard to prove that this thing is the best one.
It's not what the large deviation would give. It's not the infimum of all the weak solution of the Jensen-Varden functional, such that such that the
Right.
point is there.
That's right.
This can be done analytically, probably.
You can write it that way, but how do you solve the the minimum, right? Because we don't know all the weak solution that does this, right? We have a candidate of the minimizer, a very plausible candidate, but we don't know actually to prove that is the one.
Proving that that's the minimizer, to me, it looks like incredibly simpler than proving the large deviation, exactly because then the rest is a mess. So
I feel it's the opposite, right? Because
you feel the opposite. Okay, maybe I'm wrong. So still, if one can prove this statement for another model without, then from the rest of the proof, like, it doesn't use any integrability.
Exactly. So this is what that's what Jeremy said.
Okay.
So
okay.
Jeremy keep claiming that one should be able to do this without. That's what Jeremy said. I'm a bit skeptical. I tend to be more conservative. Yeah, but yes, you're right. If you can do this for not just this particular initial condition, but for a class of initial condition, the rest of our argument does not depend on integrability.
Because say this kind of statement, in some sense, here is said with probability. But once you know the upper and lower bound on elementary like solution, what you call it, it's just an analytical problem to prove that that one is the actual minimizer. Now, I'm not an expert on this, but say I know, like I know like a bit of geometric measure theory. There are some people who really can do incredible things with this stuff. And okay, and then so the next step is like general. From here to the end is like, that's because honestly I try to go into the paper, but I have troubles really read it because
I mean,
so they didn't
points.
understand this concept. But this is okay. But then this is a very I see. Then it's. I think there are some chances to like extend the approach to other models. This is very nice, man. Okay, thanks.
Thank you.
So, okay. Thanks.
No problem.
Are there other questions from the audience? Okay, well, maybe we should stop here. So thanks very much, Li-Cheng. Why don't we thank him again? And we'll see everybody next week. Okay, so thanks, Li-Cheng.